All right, so let's go ahead and get started. So the first of the two lectures is going to be the culmination of part 4 of the course. So remember, this is where we insist on simple auction formats, and we're asking for which formats and under which conditions, for example, on the valuations, are equilibria guaranteed to be good? Is the price of anarchy guaranteed to be close to 1? So in the last, so we've had 3 lectures on this topic so far, and for concreteness, all 3 of those have been on exactly the same type of auction format, simultaneous single item auctions. We've looked at both the second price version and the first price version. And it's been convenient to be concrete to develop our toolbox, and now we have both extension theorems and composition theorems to prove bounds in the price of anarchy. But what I want to emphasize in this lecture is that our toolbox is rich enough to cover other kinds of interesting auction formats as well. And so the first topic for today's lecture, we're going to revisit sort of an old friend and apply the same toolbox to prove some interesting new bounds. And then I'm going to show you basically how you can go beyond the smoothness framework and cover even more general settings than we've done so far. So both of these results are just from the past 3 to 6 months or so. So we're really, all of you are really completely up on the cutting edge. Okay, so let's go to the first topic. So the price of anarchy of demand reduction. So let me remind you about both a setting and an auction format and incentive issues that we were discussing in the very first part of the course. So this was in lectures, I think, 3 and 4. So this was, at the time we were calling it scenario number 4. So this was where we had identical items. Okay. And bidders are not necessarily unit demand. They want many items, but the assumption in scenario 4 is that the valuations are downward sloping. Okay, so the marginal value of each additional item is at most is non-increasing, is decreasing as you get more and more items. Okay. So downward sloping valuations, and such a valuation is specified by the marginal values of getting a jth copy of the good, a jth good. And so downward sloping just means that the marginal values are only going down. Okay? So this is the special case of the gross substitutes scenario when you have identical items. So gross substitutes was the extension of this to heterogeneous items. And let me just remind you a little bit about this scenario. So let's recall what the welfare maximizing allocation rule is, because it's very simple in this setting. And we used it back in the day, and we're going to use it again today. So suppose you knew the actual marginal valuations. How would you allocate the M items? How would you split them up amongst the N bidders to make the welfare as big as possible? Well, remember, this is just a simple greedy algorithm. So you would just sort the marginal values. You basically just sort of, right, so you have n times m numbers, n bidders, m marginal values for each of them. Of those nm numbers, you would look at the highest m of them, and those would correspond to the allocations of the m items that you've got. Okay? So really, all you'd do, you'd sort all the mij's. Okay, and depending, it may be that one bidder gets all of them. That's fine. It may be these are split amongst the bidders in different ways. So sort all the marginal values, allocate to the highest m of them. And this makes sense because valuations are downward sloping. Okay, so because the mu's are only going down as j increases, this means that by allocating to the highest mu ij's, each bidder I will get an allocation corresponding to a prefix. Okay, so it'll the highest 10 mu ij's for a corresponding bidder I will be those with j equal 1 through 10. Okay, so that's why this makes sense. Downward sloping is important for that to successfully maximize welfare. Okay, so this is the allocation rule. So suppose you wanted to turn this into a mechanism. How would you do it? Well, so we're back into settings that we understand well. So if you could just do a direct revelation mechanism, you could just run the VCG mechanism. That would be fine. Our main concern when we talked about scenario number 4 was, at the time, we were concerned about ascending implementations. So yes, there's the VCG mechanism, but we worked hard to develop this other ascending auction, the clinching auction, which at termination, assuming sincere bidding, terminated with the appropriate allocation and the VCG payments. Okay? So the clinching auction was the main thing we studied in scenario 4 a couple months ago. And one thing I want you to remember about either the VCG mechanism or the clinching auction, whichever, in this setting is that different items are sold at different prices. Even though all the items are identical, the clinching auction, for example, we had this price, the price went up over time, and as the auction proceeded, you would, as a bidder, you would clinch items successively at higher and higher prices. So you'd end up with like 10 items, you'd pay something for item 1, something larger for item 2, something larger for item 3, and so on. Okay? So to get dominant strategy incentive compatibility or ex post incentive compatibility, we had to sell the items for different prices. Okay? So that's what we did in scenario 4. Now, to motivate the clinching auction, what I did is I actually said, well, let's do something even simpler, okay, and see where it goes wrong. Okay? And where it went wrong is what motivated the VCG mechanism. So even simpler than the clinching auction, the VCG mechanism would be, well, all the items are the same. Let's just sort of draw a supply curve and draw a demand curve, wait till they cross and set the price where they cross. Okay? So in other words, in addition to the clinching auction, our punching bag in that lecture was uniform pricing, which was if you're given bids, so I'm going to call the bids BIJs, you just sell to the highest or the top BIJs at a price equal to the m+1th highest bid. Okay? So in other words, so this mechanism has exactly the same allocation rule, okay, as VCG, or as we said over here. Given the BIJs, you allocate according to the highest M of them. But the payment rule is different and simpler. Okay? So VCG, the clinching auction, you charge different things for different items. Here we're going to charge exactly the same thing. If you're going to charge exactly the same thing for all of them, well, inspired by the Vickery auction, one thing you might try to do would just be to take the highest losing bid, and that sets the price for everybody else. Okay? So this, I hope, is all review. Okay? Another thing we were sort of using to illustrate at this time, this is also when we were talking about Walrasian equilibria. And so you can think of uniform pricing as basically trying to implement the smallest Walrasian equilibrium in a mechanism. So in this identical goods setting, the Walrasian equilibria, so that's just the price where the market clears, those are just going to be all the prices between the mth highest and the m+1th highest Bij. So this price corresponds to the smallest of the Walrasian equilibria. Okay? And we were just coming from settings where all the lowest Walrasian equilibria, in fact, gave us incentive compatible mechanisms, unit demand bidders, and we used this mechanism to illustrate that that doesn't continue to work when you have identical items. Okay? Let me remind you why this doesn't continue to work, why this isn't incentive compatible. It's because of something called demand reduction. So even suppose m equals 2. So again, the point of this example is just to show that in the mechanism where you use the welfare maximizing allocation rule and you use uniform pricing, it's not dominant strategy incentive compatible. Okay? You allow players to report downward sloping valuations. They have the option of telling the truth, but they're not going to in general. So why? Well, just suppose you have one additive bidder and one unit demand bidder. Okay? So bidder 1 is additive. It gets 3 for each item that it gets. And bidder 2 is unit demand. So it wants one item for a value of 2, and it has no marginal value for a second item. Okay? So the claim is that the first bidder does not have an incentive to bid truthfully. Okay, so assume the second bidder does bid truthfully. So why not? Well, if bidder 1 did bid truthfully, how many items would it get?
2.
It would get both, right? What would be the price for each one?
2.
Also 2, right? So there's sort of 4 if all the bids are truthful, well, in any case, there's 4 bids, 4 BIJs, there's M goods, the top 2 win. With the truthful bids, these will be the winners. What's the clearing price? It's just the highest losing bid. This is the highest losing bid, okay? And so that's what would happen. Bidder 1 tells the truth. It would get 6 value, but it would pay 2 each for a utility of 2, okay? Suppose instead that bidder 1 engages in demand reduction. That is, it replaces this with a 0. It replaces mu 2 with a 0. It says, actually, I'll just pretend to be unit demand, and my value is 3, okay? So now in the allocation, so now that the second thing's a 0, the highest 2 bids are the first unit bid from each bidder, 3 and 2. So those are the winners. Each bidder gets exactly 1 unit. And allegedly, nobody wanted a second unit. Okay, so the highest losing bid is 0. Okay, so we just give both goods away for free, 1 to each bidder. So then bidder 1, it gets fewer items, only gets 1, but it pays nothing. So its utility is 3, better than 2. Okay? So that's demand reduction, and it's real. And you see this in practice when people implement this auction, and sometimes they do. Bidders have an incentive to get fewer quantities than they would otherwise want because they wind up getting it at a much cheaper price. And so overall, it's a win. Okay? So number 1 would prefer 1 unit at price 0, which it gets with a false report, over 2 units at price 2 each, which would give it only utility 2. Okay? So that's a concrete demonstration that the uniform pricing mechanism is not DSIC, okay, because of demand reduction. Right? But now that we're in this part 4 of the course, maybe we were tempted to say, well, so what? Maybe we want to use this anyways, okay? So now we have a toolbox for reasoning about mechanisms which are not truthful, okay, which are not DSIC, where we don't even know what bidders are going to do, okay, where we can't even solve for equilibria. So maybe actually this simple mechanism, maybe its equilibria are pretty good anyways, and then maybe there are contexts in which we want to use it, okay? So that's the first half of this first lecture, is the price of anarchy of demand reduction. Okay, so what's the price of anarchy of this mechanism? So any questions up to that point? Okay. And then a quick full disclosure, so of the 2 lectures we're going to do today, right, so the first one is the last lecture of a part, so this first half is going to be kind of a little on the technical side, but comparable to last week. And it might be a little bit longer, it might be more like 90 minutes, but then the second lecture, being the introduction to a new topic, is going to be shorter and easier, okay, so just so you're duly warned. All right, so here's what we're going to prove. We are going to prove a bound on the price of anarchy of demand reduction. And so I'm going to show you sort of a blend of 2 papers just from the past few months. I'll put links up on the website. So you might recall from simultaneous single item auction discussion, for the second price rules, we had these no overbidding conditions, which were necessary for good bounds. And here, this has the flavor of a second price auction. Right? So we're not charging people what they bid, we're charging them something that could be quite a bit less than what they're bidding. So again, the guarantee will be under a no overbidding assumption. So with no overbidding, we're going to prove that the Bayes-Nash price of anarchy is a constant, bounded below by a quarter. And this is going to be actually even for correlated prior distributions. Okay, which is pretty cool. We've seen almost no results for correlated priors. The only one we ever saw was when we talked about a single item auction with the first price rule. Okay, so we're going to see a second example of that today. Okay, so that's the main result. So demand reduction, while definitely, as we know, can affect efficiency, at equilibria it can only affect you so much. All right? All right, so what we now know, we have this toolbox of extension theorems, and I'm not going to go back over them again. We know that proving bounds like this just boils down to proving a suitable smoothness condition. So I'm just going to state the smoothness condition. It will be familiar from the last several lectures. Okay? So it boils down to the following smoothness condition. So what we want to prove is that for every valuation profile, mu, there exists hypothetical deviations, which are allowed to depend on mu. such that, and again, this is exactly the same order of quantifiers we've been talking about the last couple lectures. Okay, so it's okay if you don't remember the details, but this is exactly what it was before, just trust me. So we're given a valuation profile. We sort of figure out how to deviate. What we were doing in simultaneous second price auctions is we were saying, well, compute the optimal allocation for this valuation, look at the items I'm supposed to get in the optimal allocation, and now bid all in for that allocation. Those were the B stars we were talking about last time. Okay, so for every valuation profile, figure out deviations B star. And then remember, smoothness conditions, you're always proving some inequality with respect to every possible bid vector B, whether or not it's in equilibrium, such that for all bid vectors B, and then it's this disentangling inequality, okay? So we say, well, let's look at the utility of people after they deviate unilaterally. And we want, so this is an entangled version of the deviations and of this arbitrary bid vector B, and we want to disentangle it. We want to say it's at least, in this case, we're going to say it's at least half of the opt welfare for the valuation profile under consideration. And then as usual, it's going to be the sum of all of the winning equilibrium bids. Okay, so again, this is going to be exactly the same as what it was before. So here's going to be the notation. I sum over the bidders. I'm going to look at how many, okay, so XIB, this denotes how many copies of the item bidder I gets in this bid profile. So it's going to be like 7 items, something like that. And then I just look at the bid that the player submitted for each of those copies. Okay, so this is the sum of the bids submitted by bidder I on the items that it wins in the outcome. Okay? And again, all of this is exactly what it was last time. All right? So we're going to call this star. And I'm just going to ask you to verify offline or recall, if it's fresh in your mind, that if we prove this inequality, then we're going to get this bound. Okay? Okay, we're going to get this bound assuming that we have no overbidding. So no overbidding just asserts that this is at most sum over j equal 1 to xi of b of the marginal values. Okay? And recall that the way we use no overbidding conditions is that allows us to take this error term upper bounded by the welfare in B. That's the term that winds up getting subtracted and then divided back through. Okay? So it's all the usual maneuvers. So if we can prove star, then we get our bound of 1/4. Yep?
Do we have any idea how bad it gets if we do allow overbidding?
Yes. And in fact, I mean, if I was still doing exercise sets, this would be an exercise. It's at that level of easiness. And actually, if you go back and you stare at the proofs, it's quite clear. So if you overbid by most a factor of gamma, then this bound is going to degrade in some linear way in gamma. Yeah, so the proofs just wind up working very nicely. Yeah. So certainly people are not, I mean, certainly if people are overbidding by 10, 20%, then all of the qualitative conclusions are totally exactly the same. If they're overbidding by a factor of 10, you still have a constant, but it's not looking like such a good constant anymore. Yeah, good question. Okay, good. So assuming this no overbidding condition, assuming we prove star, we'll get the bound of 1/4. Okay, and it's exactly like the simultaneous second price auction analysis. There we had a 1/2. The reason we got a 1/2 there and we're getting a 1/4 there, for simultaneous second price auctions, we did not have a 1/2 here. We just had a coefficient of 1. So this extra coefficient of 1/2 is why we're getting a 1/4 instead of the 1/2 we got 2 lectures ago. Okay? All right. So any questions about that? So the rest of this part of the lecture is just going to be, I'm just going to show you the B stars, which gets you inequality star. Okay? Oh, and then I forgot to say, right, so that's how, okay, so that's how you get, the 1/4. For what equilibrium concepts do you get them? Okay, so we saw a bunch of different extension theorems for Bayes-Nash equilibria in the last couple lectures. There were sort of 2 main different ones. And it boiled down to how these B stars are chosen. The one that you've seen mostly, remember we have these canonical B stars in mind, like you compute the optimal allocation and then you go all in for what you're supposed to get in the optimal allocation. So then the B stars depend not only, B star I depends not only on VI, it depends on the full valuation profile. Right, so to compute the optimal allocation, it's not enough to just know what my valuation is. I need to know everybody's valuation to compute the optimal allocation, okay? And so then, for deviations defined in that way, where B star depends on the full valuation profile, we're able to extend the price of anarchy bounds to Bayes-Nash equilibria for an arbitrary product prior distribution. So we had to assume that the valuations were independent. And the proof where that showed up is we had to use this doppelganger trick. So for a bidder to be able to actually execute B star, it had to have some imaginary valuation profile. Remember, when you reason in a game of incomplete information, you only know your valuation, you don't know the other people's valuations. So B star is not defined if you only know your valuation. So you just make some up. You just sample some from the publicly known prior distribution. That's the doppelganger trick. And we had a non-trivial proof that extended the Bayes-Nash price of anarchy bound to product prior distributions. There's this one case, okay? This was, I called it corollary 2 last lecture. It was just a single item first price auction. And we could get away with super simple B stars. Everybody just bid half their valuation, okay? And you can bid half your valuation without knowing anything about other valuations. And what we saw is that in that simple type of B star, simple type of deviation, where it depends only on your valuation, VI, and not on others, not on V minus I, you actually get the extension theorem for correlated distributions, for totally arbitrary prior distributions F. Okay, that's what we proved. That was actually a much easier proof. That was basically just linearity of expectation. Okay? So that's the thing to remember. We have 2 genres of extension theorems. If B star depends on the full profile, you get it for product priors. If B star I depends only on I's valuation, you get it for correlated priors. So by stating this for correlated priors, what you should be sort of anticipating is that I'm going to show you hypothetical deviations B star, where B star I depends only on, in this case, mu I. Okay? That's what's going to enable the extension theorem, which should get me this conclusion. And that's what I'm going to do. Okay? All right, so that's the recap of how you compile smoothness conditions like star into Bayes-Nash price of anarchy bounds. Okay? And again, it's just exactly the same as before, so I'm just going to show you this. And to show you this, I just need to show you the B stars. Okay? Everyone clear? So once you get used to this whole template, it becomes very, algorithmic, basically. I mean, there's just this way that you prove bounds like this. Just show me the B stars. Okay? Okay, good. So the B stars are maybe not the first thing you try, but they're the second thing you'd try. Okay? So let me explain. All right, so far, what everything I've said sounds the most like is second price auction, simultaneous second price auctions. Right? We have this no overbidding condition, we're charging people less than their bids, etc. And so what did we do what were our B stars in that case? Well, like we said, you compute the optimal allocation and you go all in for the optimal allocation, where in that context, we had these XOS valuations. So going all in, you just looked at the relevant additive valuation that met your optimal bundle, and that sort of told you how to bid on the different items. So here it's simpler. That high-level idea is simpler. Compute the optimal allocation, go all in on the bundle you're supposed to get. Here's the first thing you'd try to implement that conceptual idea. So you just bid your value up to the number of items you're supposed to get in the optimal allocation, and then you just bid 0 everywhere after that. Okay? So this is a deviation that depends on the full profile. Okay, I look at the full profile, I compute the number of items I get. That's this notation. So this notation is for the profile mu, how many items do I get? So this is just a number like 7. And then I bid truthfully up to the number of items I'm supposed to get. That's going all in for them. And then I bid 0 after that. Okay? This, I think, would be the first thing you would try, given what we've done so far. Okay. So I'm not going to do the details of this. I'll leave it as an optional exercise. It's not hard to prove that this is too aggressive a deviation. And it doesn't work. It doesn't work in the sense that, so remember, we need this smoothness inequality star to hold for every single bid vector B. So by this not working, what I mean is that I can exhibit some, frankly kind of weird bid vector B, so that because these bids are so high, You wind up winning items, but you pay your full value. Okay, so we had a similar thing happen with the first price auction, okay, where the first thing we tried was like, well, what if you bid your value? And the first price auction, well, but then if you win, you pay your value, your utility is 0. So the left-hand side was 0. Didn't work for the first price auction. For similar reasons, it's not going to work now. Okay, this might be 0, even though the right-hand side might be big. Okay, so there exist bid vectors B for which that's true. So that's the first thing I think you'd try, given the analogies with the simultaneous second price auctions. But then once this doesn't work, and once you realize it doesn't work because it's sort of too high, too aggressive, because on the left-hand side you eat up all of your utility, all of your value with what you pay, you're like, well, you know, for first price auctions we had that problem, we just cut it in half. So that would be the next thing we'd try. Let's just try to use the first price auction trick. So idea number 2, cut B star I in half. Okay? And this works. So this works just fine. You can prove this inequality star for these B stars. Okay? And it's going to be by basically the same proof I'm going to show you. But I'm going to show you that proof not for these B stars, because there's an even better idea. So remember, if you look at this, we said there are these 2 types of deviations. Those that depend on the full profile and those that just depend locally on your own value. This is of the former type, right? Because I'm computing how many items I get in the optimal allocation. So that depends on the full valuation profile mu. If we want a conclusion for correlated priors, I want it to just depend locally. And there's actually a very simple way to do that. Any ideas? So what's like a version of idea number 2 that doesn't depend on everybody else's valuation? Any guesses? So we're just going to use mu I, the values, the marginal values, cut in half. Okay? So just like in the first price single item auction, you just bid half your value. Okay? Now, frankly, we would have loved to have done this in the simultaneous single item auctions. That would have been cool, right? We would have loved to have gotten away with that. But if you think back to that auction format, that wasn't an option. Simultaneous second price auctions, the whole point of it was you have this valuation space bigger than the bid space. We're thinking about bidders that have like submodular valuations, but I don't listen to your submodular valuation. I force you to submit just 1 bid per item. You have 2 to the m things to say, I only let you say m of them. Okay? So you didn't have the vocabulary to express a bid of half of your valuation for simultaneous single item auctions, unless of course you have an additive valuation. Here, we don't have that issue. I mean, this is a simple auction format, but the simplicity does not come from having a bid space strictly smaller than your value space. In this uniform pricing auction, you're permitted to report any downward sloping valuation you want. Okay, so certainly reporting truthfully over 2 is an option. Okay, and we're going to use that. So that's why we're going to be able to get an extension to correlated priors here, whereas we didn't for simultaneous second price auctions. We can get correlated in effect because the bid space is rich enough to express valuations. Okay? So that's what we're going to do. Right? So what remains to show is that for this choice of B star I, star holds. And then we're done. And that's all I'm going to say about the price of anarchy demand reduction. This proof. Okay? So are we cool up to here? All right. So, proof of star. So, fix an arbitrary bid profile B. Again, star has to hold no matter what B is. Consider one of these summands on the left-hand side, and let's try to get a lower bound on it. Okay, so fix your favorite player I. So we're going to use the fact that the allocation and the prices are computed in such a simple way. Okay, so let's just remember the picture. So a couple things. So first, just remember this B star I. This is just mu I over 2. And then the other thing to remember, okay, so the allocation rule, so the mechanism is going to have these sorted, high to low. So these are going to be all the inputs to the mechanism, all the Bij's. And it's going to allocate to the top m. And then the m plus 1th guy sets the price. Okay? In the uniform pricing mechanism. Now, from I's perspective, what is I submitting in this profile? It's submitting its valuation, its marginal valuations divided by 2, and its marginal valuations are decreasing. So the highest bid that player I submits in this outcome is its bid for the first item, which in this deviating bid, bidder I says it's willing to pay mu I1 divided by 2 for the first item. Okay? That's what's happening, the outcome that we're looking at. And then, maybe there's some other bids, some BKJs that are higher. Then there's some more BKJs in between the next highest bid belonging to player I, which is going to be its alleged value for the second item, mu I2 in half. And then there's going to be, some various mu IJs that don't make the cut. Okay, so maybe mu I3 divided by 2 is over here. Okay? And then in between, so these are BKJs for the other players. Whoops, K not equal to I. Okay? So that's the picture you should have in mind. Okay, sorted from high to low, top M are allocated. First losing one sets the price for all of the items that are allocated. Okay. Now, I'm going to do something just for technical convenience that's a little weird, but it just smooths the proof out. So, all right, so in this profile, the other n-1 bidders are doing what they were doing in B. Bidder I switched from what it was doing in B to this deviation B star. Okay? For the analysis, I'm going to pretend as if there's still a copy of bidder I submitting its old bids in B. Okay? So the claim is, if I look at player I's utility, after it deviates to B star and the other n-1 players are still doing whatever they're doing, that can be lower bounded by its utility with its same action. After I add some n plus 1th bidder to the auction, who's bidding exactly how I used to be bidding in the original profile B. Okay? But more generally, just imagine this picture. Okay? So imagine that there's the other n-1 players doing what they were doing, and then there's bidder I submitting these mu's over 2. And now imagine I just insert some more bids, okay, into this array. Okay? The claim is this can only be bad for bidder I. It can only decrease its utility if I submit some more bids into this array. Okay, and it's sorted, remember. Because what are the implications from I's perspective if I throw in some more bids? Well, first of all, there might be some items that used to make the cut in the top end that get pushed out of the top end. Okay? So whatever items I used to be winning, which were giving it non-negative utility, now it doesn't get them at all. Okay, so that's bad. The second thing is as I throw in some more bids, remember this is sorted, the price is only going to be going up. Okay? Right? This number is only going to get higher as I throw more things into this sorted array. Okay? So you win fewer things, and whatever you're still winning, you win at a higher price. So your utility clearly drops when I insert more bids. And again, for convenience, what bids am I going to insert? I'm just going to insert the original Bij's. And don't worry about why. Okay? So this is just the claim. So I'm actually going to lower bound these. All right? Okay, so the bid vector B is there, and now I've inserted this sort of new player that's bidding according to B star. I want to lower bound that new player's utility. Good. All right, so we need to compare, so we need to relate things to the optimal welfare, right? That's always the point here. So what's going on in the optimal allocation? Let's say I gets X star I items in the optimal allocation for our fixed valuation profile mu. And let's say it gets Xi items in the outcome under consideration. So B star, and again, remember this is just mu I over 2, okay, always. All right, so that's the notation. X star is what bidder I gets in the optimal solution. Xi is what it gets in what we're dealing with right now. All right, so let's start with an easy case. Or let's just observe something really nice about our particular deviating bid mu star. Okay? So, excuse me, not mu star, mu I over 2. Okay, so B star I is mu I over 2. So suppose you win an item with this bid. Okay, so you bid mu I over 2. I claim every item you get, you're really happy you got it. Okay? So you get significant utility from every single item that you win with this bid. Okay? Because you bid only half your value. You pay at most your bid. So the payment eats up at most half of your value for the item. So you're left with utility at least half of your original value for the item. Okay? So that's this nice sweet spot that these values over 2s represent. Okay? Because you're not going to pay more than that, you're insured of getting high utility for every item that you win. So every item j I gets in mu I over 2b contributes at least mu I j over 2 to i's utility. Okay? Why at least mu I j over 2? Its value is mu I j over its value is exactly mu I of j. Its bid is exactly mu I j over 2. Its payment is at most that, so the utility is at least this, what's left. Okay? So a really easy case for us then is any bidder that when it deviates via mu I over 2, if it gets a lot of items, it's really happy. Okay, so remember what we're trying to do. We're trying to say that these are big. We're trying to lower bound. Ultimately, what we want to do is we want to lower bound utilities to the equilibrium. So we're doing that by lower bounding utilities when you deviate in this way. And so if you get a lot of items when you deviate in this way, then you're going to be happy. Okay? So precisely, for any bidder I, where it gets at least as many items after deviating as it's supposed to get in the optimal solution, then this, right, just using this fact, I'm even going to throw out anything beyond the first X star I that you get. I'll just sum up your utility contributed by the first X star I items that you get. And by this observation, it's at least this. Okay. And this is just I's welfare in the optimal allocation by the definition of X star I. Okay? So again, this is just meant to be an easy case. Right, so any bidder, when they deviate, they get at least as many items as they're supposed to get in the optimal allocation. Because item by item, they get high utility, at least half their value. That means their utility is at least half of the welfare in the optimal solution. And that is actually way better than what we're even trying to prove. Right, so we're trying to prove that the sum of the utilities post-deviation is lower bounded by half of the welfare minus some error term. Okay, so for bidder I in particular, we just prove star without an error term. Okay? Is that clear? So this is an easy case where we're getting even more than what we want. Okay. All right. So the real case, so the interesting case is where you have this carefully crafted deviation, you're bidding half your value, but then when you actually deviate that way, you just don't get many items. Okay? So now it may not be that it may not be that your values are high. You may get, in fact, even think about the case where xi is 0. You might want to keep that in mind in the following derivation. Okay, so imagine you switch, you say mu I over 2, and you get nothing. Okay? So it's obviously not the case that your welfare is high. Your welfare is 0. Okay? But so we want to somehow have the error term involved. We want to basically say that the welfare that we're supposed to get is being sort of instead, we can charge that in effect against bids by other bidders. Okay? All right, so suppose the post-deviation you get fewer items than the optimal solution. Again, think of xi equal to 0 as a canonical special case. So what do we got going for us? So we want to lower bound the utility. So let me write it this way. So there are some items you get xi items. And we argued that for any item you get under any circumstances, because your bids aren't that high, your utility is high. Okay? So you're happy for the xi items you get with the deviation, for sure. So now let me write it this way. Okay, so imagine, maybe in the optimal allocation you're supposed to get 6 items and you really only got 3, okay, once you deviate it. So for items 4 through 6, here's the way I'm going to think about it. So for the items that you're supposed to get in the optimal allocation and you didn't get here, why is that? Okay, it's because you're after the cutoff. Okay, so items 4, 5, and 6, if you only got 3 items, and you're wondering about why you didn't get items 4, 5, and 6, it's because, mu I 4 over 2, mu I 5 over 2, and mu I 6 over 2 were all here. Okay? So they didn't make the cut. So what I'm going to do is I'm going to say, okay, well, if they didn't make the cut, then I'm going to point to bids in the top M which did make the cut. Okay? Those are at least as high as my bids which did not get allocated. Okay? So for items 4, 5, and 6, I say, well, let me look at what I bid for that particular item. And remember, this is what you're bidding on the jth copy of your item. And because you lost, that means there's some other bid that did make the cut, which is higher than your bid. And so what I'm going to do is I'm going to charge. So say for the 4th item, I'm going to charge it to the lowest bid that made the cut. For the 5th item, I'm going to charge it to the 2nd lowest bid that made the cut. For the 6th item, I'll charge it to the 3rd lowest bid that made the cut, and so on. Okay? So, so this was what you bid. You lost out to somebody else. And this is going to be what I'm going to charge it to. Okay, so again, the way to think about this term is it's just some bkj that made the cut and therefore is bigger than your bid. Okay? So that's the claim. Okay, or this is true in general. So when you deviate in this way, for the items that you get, this is a lower bound on your utility for the xi items that you actually get. Here, for every j, this is non-positive, okay? Because you lost and this guy won. Okay, so j by j in this range, this is non-positive, so of course I can add this in, and it's still a valid inequality. Okay? All right. So why did I write it this way? Well, it's because I need to lower bound this deviating utility with respect to the optimal welfare. So I can group these two terms together. So this is equal to the welfare of bidder I in the optimal solution for the profile mu minus, so here's what I'm going to do. Right, so I've gotten rid of that term, right? I just combined that with the first sum. I'm going to subtract something even bigger. Sorry, so this is going to be less than or equal, greater than or equal to. I'm going to subtract something even bigger than this. I'm just going to let the sum range from 1 to x star I. Okay? All right, so I'm just adding more terms. So I'm subtracting something even bigger. And now the claim is we're done. So the claim is star holds. So summing over all of the bidders, so this is true for every bidder I. So summing over I. So obviously this part is just the optimal welfare, or half of the optimal welfare. I get that bidder by bidder. So let's look at this expression. Okay, so if we stare at this expression in exactly the right way, all right, what do we want it to be? We want it to be, the claim is that it's going to be, that sum is upper bounded by the sum of the highest m bij's. Okay, so I'll argue that in a second. That sum, the error term, is bounded above by the sum of the m highest bij's. Let's just observe that if we prove this, this is exactly the same as the smoothness condition. Okay? So that term's exactly the same, this term's exactly the same. All right, so what is this last term? This just says, look at the sum of the winning bids. Okay? And the allocation rule gives it to the highest m bij's. Okay? So this term is also exactly the same as this term. Okay? So why is the sum of this over I bounded above by the sum of the highest bij's? Well, consider the highest bkj's. Okay? Sorted from high to low. All right, so this is the highest of all of the nm bids. This is the mth highest of all of the nm bids. So what are we doing here? Okay, so say x star I is like 10. What this sum is the tail of this sorted sequence. Okay, it's the sum of the last 10 entries in this array, if x star I is like 10. Okay? So that's just what this is by definition. Now, when we sum over the bidders, okay, the sum of the x star i's, remember x star I is how many items somebody gets in the optimal allocation. The sum of those allocations is m. All m items are allocated. So really what we're doing as we sum over I is we're just saying, okay, it's upper bounded by the lowest 10 of these, plus it's upper bounded by the lowest 13 of these, if player 2 gets 13 items in the optimal allocation, plus the lowest 5 of these, and so on. Okay, so that's what these terms are as we sum over I. So we charge a total of m times to this array, and we're always charging to the lowest entries in this array. Okay? So we charge m times to only the lowest entries. Certainly it's only more if we charged exactly once to each of the entries. Okay? So that's the proof. All right. Using the fact that the sum of the xi stars equals m, and the fact that we only charge to the smallest entries in the array. So any questions about that? Okay, then let me just mention, I'm not going to write any more down on this point, but just a couple variations. So first, let me just emphasize, the B stars we used indeed depended only on mu I, not on mu minus I. You just bid half your value. So we do get the factor of 4 all the way out to the Bayes-Nash equilibria of correlated distributions. If you want, you can equally well do a pay-as-bid version of this. So you can have the same allocation rule, but you can just analyze it as if you pay exactly what you said you're willing to pay for each of the items. For the exact same reason that you could cancel out the revenue terms with the bid terms in the simultaneous first price auction analysis, in the same way you can cancel those terms here, and you should get a factor of 1/2. The paper doesn't claim that for some reason, so maybe I'm missing something, but I'm pretty sure this should improve to a 1/2 for the pay-as-bid version. And one thing that's cool is you can even extend this to scenario 5. So this was identical goods, downward sloping. Pretty much the same analysis works if you go all the way out to gross substitutes. So this is now non-identical goods, bidders' valuations are gross substitutes, And again, the bid space is gross substitutes. So if you think about it, this is basically like, instead of analyzing the uniform price auction, this is something like analyzing Kelso-Crawford. So Kelso-Crawford was this ascending auction. We only analyzed it assuming sincere bidding. We argued that in fact sincere bidding is not incentive compatible. So you could ask the question, what happens in Kelso-Crawford if bidders do whatever they want? And this equilibrium analysis basically says you still get this factor 4 for Kelso-Crawford. Okay, so it's not incentive compatible, but again, assuming no overbidding, the equilibria are good for Kelso-Crawford. So that's actually very satisfying that, these are auction formats, right? We talked about at the beginning of the course, but really they're like 30 years old. These are results that are just a few months, which finally kind of push beyond the sincere bidding and actually do a proper, analysis of the, cost of incentives, right? So how much welfare do you lose when you take incentives into account for those 30-year-old auction formats? So that's pretty satisfying, okay? You have to do a little bit more work. So, so where we were really using the identical items, was when we were saying, oh, the allocation rule is super simple. You just sort it in this array, and then you can do these charging arguments. That part is much more complicated for gross substitutes, but still the proofs aren't that much more technical. Okay. All right. So any questions about all that? Okay.